All right, so let's get started. My name is Eric Broomer. I'm a developer on the C++ compiler team. Mostly been doing compiler optimizations, been at Microsoft for almost 7 years now. And this talk's going to be different than the other talks that have been going on at Build so far that you guys have probably seen. We're not going to be doing app development or stuff like that. We're going to be doing a very, very deep dive into native code performance. And sort of what does that mean and what's changed in terms of native code performance when we're talking about modern processors. So let's dig right into it. Yes, new CPUs have new instructions. These are a whole bunch of different instruction sets that have come alive in the last decade or so. You may have recognized some of them. Don't worry if you don't know what they all are. We're going to touch on a few a little bit later. A cool one that's sort of been heralded as going to be the savior for scientific computing is fused, multiply, accumulate. Has anyone heard of FMA, fuse, multiply, FUMAC, FMAC? Okay, a decent number, not as many as I was thinking. So FMA is really, really cool. It lets you do, it's just a handful of new instructions. They let you do a multiply and an add at the same time as it just takes to do a single multiply. So you get all this extra stuff for free. Right, this is a new instruction set that's in modern processors that's supposed to give you all this performance for free. Well, what if I told you that if you use FMA everywhere, it's going to be a detriment to performance? We'll touch more on that later. Something completely different. Let's take a look at this code here. So this code is just two 128-bit copies, right? We're loading y sub 0, you load that and you store it into x sub 0, you load y sub 1, and you store that into x sub 1, where each of those things is an individual 128-bit copy. And we are going to take advantage of 256-bit stuff that exists on newer processors. We are going to optimize this to just do a single 256-bit copy. This seems like something that would be awesome, right? There's these 256-bit instructions, let's take advantage of them. Well, what if I told you that this particular optimization can cause problems, huge performance problems on some chips, but not on others? Things get weird. So what's going on? Why is reasoning about code performance strange with modern CPUs? Right, I just gave you two very, very quick examples. We're going to touch on them much more later. We're going to go pretty deep later. But why are these new instruction sets coming out? When you take advantage of them, you could potentially really hurt your performance? That's not cool. What's going on with that? So we're going to spend this hour and go deep into what it means to achieve performance out of modern CPU instructions, and what are the pitfalls, and what are some of the tools that you can use to really get that extra performance that's being heralded with all these new instructions. But first, I want to talk just very briefly and sort of level the playing field in terms of what do I mean by modern CPU instructions. So this big arrow is the standard line, meaning this is going to be a timeline. And way back in the day, Intel Pentium 3, 1999, and in 2001, AMD released the chip that supports the SSE instruction set. This was some 128-bit instructions, not all of them. It wasn't a full instruction set for 128-bit stuff. It was just some of them. The switch that you could throw to enable optimizations targeting this was the /arch SSE switch. I was in high school when this came out. I don't know what version of Visual C++ this actually came in. It predates Visual Studio, so it's definitely a Visual C++ branded product. And the switch predates the last two versions of source control that we use in the compiler. So I'm trying to search back and I just can't find it. So I don't know when this Arch SSE switch was actually introduced. Somewhat more recently, we're talking SSE2 stuff. So right, that started in the Intel Pentium 4 around 2000, 2001, the AMD chip as well in 2003. Visual Studio.NET 2003 gave us the Arch SSE2 switch, which really rounded out the 128-bit vector instructions. Fast forwarding a little bit, we've got the AVX instructions. That's Intel Sandy Bridge that came out a few years ago, as well as the Bulldozer. And this gave us some 256-bit instructions. And the Switch Arch AVX gave optimization support for that in 2010. And I am happy to say that with Visual Studio 2013 Update 2, which you can get right now, we've added support for Arch AVX 2. Which is the Intel Haswell chip that came out last year. We've had intrinsics that you could use the Haswell instructions if you wanted to code them with intrinsics, but with 2013 update 2 with the /arch AVX2 switch, we are optimizing your code to target AVX2. So when I mean modern CPUs, I just mean the stuff on the right. But now we know what's this SSE, what's this AVX business, and some sort of history, some sort of timeline stuff. Yes, okay. Generally, the question that I'm going to get here is, well, what about all the other stuff? What about SSE2, SSE3, SSE4, or SSE3, 4, 4.1, 4.2, SS, SE3, all that kind of crap? Yes, processor companies definitely did stuff between 2001 and 2011, but we didn't have direct optimization support through an Arch switch for that. That's why I left them off of this particular chart. Yeah. Yeah, my team's been working really hard on Arch AVX2 support, so I'm pretty happy with it. Okay. I've given a decent number of talks, and I've got to say this is by far my most favorite agenda slide. Thank you. Okay, so what are we going to talk about in this? We're going to talk about three things. Number one, we're going to talk about using new instructions and where you can get some pitfalls from dealing with fuse, multiply, accumulate. Number two is going to be a statement, I think a bold statement about performance. And number three is going to be digging into a performance bug, which I think is super, super interesting. But first, before all of that, I want to make sure that you guys can take something out of this talk, take a set of tools, or at least a way of thinking about performance that you can apply to your job. I don't want this to just be me describing what's hard about working on a compiler, or what's hard about, targeting new processor architectures or stuff like that. I really want you guys to take something away from this. And what made sense to me in terms of what tools should you take away from this, what mindset should you take away from this, all has to do with profiling. So anyone who's spoken to me at the booths in the last few days, almost always the conversation is going to turn into profiling when we're talking about performance. Those two things go hand in hand. Profiling your code is the true way to measure speedups. If you want to decide, hey, I'm going to rewrite this particular thing using AVX2 intrinsics, you better take a profile before, you better write the code, and you better take a profile after. That's the only way to make sure that the speedups you're getting are actually because you wrote them that way. And similarly, if you get a performance loss for doing whatever, you have to profile your code to figure out what's going on. Some profilers, there's the Visual Studio Performance Analyzer, which is great if you're looking at things sort of at the function level, or if you need to track things like I/O. By I/O, I mean sort of disk access, multi-threaded stuff. The Visual Studio Performance Analyzer is really good at that. If, on the other hand, you need hardware performance counter information, which a lot of the time you do for really low-level stuff, which is what we're going to be talking about today. If you're on AMD chips, the AMD CodeXL product is going to be really useful. If you're on an Intel chip, the Intel VTune product is going to be really useful. Okay, let's get started. So FMA is really, 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 really cool. It's fuse, multiply, accumulate. You could hear it FMA, FMAC, FUMAC, whatever. They're all basically the same thing. If you so wanted, you could access these instructions directly by writing with intrinsics. So if you're forced to write intrinsics, or if the compiler's not giving you exactly what you're expecting, you think you can do a better job, go ahead, write the intrinsics. If you enjoy scraping your eyeballs out with a rusty spoon, you can use the intrinsics. That's sort of there, or you could throw the Arch AVX2 switch, and we're going to do the right thing for you. Okay, I've probably pissed off a whole bunch of people right now. So people do write with intrinsics. I write code with intrinsics, and it's not fair for me to say something like that. So what intrinsic code does, my boss calls it Klingon. So you're reading and writing Klingon, which is totally fair. I think there's an instruction called fnmad. F-in-mad. That's sometimes how I feel when I'm reading instructions. Sorry, that was a terrible joke. I thought of that this morning at like 5 a.m. when I was waking up. I'm like, maybe there's F-in-mad somewhere. But seriously, writing intrinsic code is actually kind of zen. right? It requires 100% focus. You know exactly what you're doing. You know exactly the performance improvements you're expecting. I'm going to write this intrinsic stuff, and it's going to work. Congratulations. 2 years later, though, right, when you've got a bug in your product or someone else had to take over your sources and fix something or make it better or whatever, or change the intrinsics to use the next round of intrinsics, that's when, you know, scraping your face with rusty cutlery comes into play. Okay, so what I really want to get at is this. So the deal with FMA is to look at what happens, why is it going to make your code go faster? And what it comes down to is a floating point multiply takes 5 cycles to execute. So a result of the floating point multiply is only going to be available 5 cycles after the multiply actually started. And a floating point add is 3 cycles, but this fuse, multiply, accumulate, the thing that does a multiply and an add takes the same amount of time it does to do a multiply. You're getting that add for free. I like free stuff. I want to use FMA everywhere. Why wouldn't you? Totally, why wouldn't you? So we did that in the compiler, and we built a whole bunch of stuff, and we ran all of our benchmarks, and, you know, things slowed down. Not across the board. We got some things that sped up, but we got a tremendous amount of things that slowed down. And I was effing mad. And, you know, trying to dig and see what's really going on, I opened up the Intel Software Optimization Guide, and I swear this is a statement nestled deep in there. This is verbatim what's written. There may be situations where using FMA might not deliver better performance. Like, well, okay. So we spent some time and really went deep into what's going on, and I want to do that with you guys as well. And the way I want to do that is using a handful of examples. So I've got the same code written 2 ways. On the left-hand side, there is this code written without using FMA, just using normal multiplies. And as on the right-hand side, we're using FMA. So show of hands, who thinks the no FMA code runs faster? Okay, handful, okay. Show of hands, who thinks the FMA code is going to run faster? Okay, we've got more people. Okay, that's good. This is not a trick question. This is straight up, right, the point of FMA. And the way of looking at this is you can just draw the tree of dependencies of what's going on. This is internally what we do with the compiler. So, you know, on the left-hand side, you're multiplying A and B, and you're adding C to it. Congratulations. On the right-hand side, you're doing A times B plus C using a single FMA operation. And you can basically just count the cycles based on this dependency tree. So on the left-hand side, 5 cycles for the multiply. The add has to wait until the multiply is finished. Then the add takes another 3 cycles. The thing on the left takes 8 cycles, whereas the thing on the right side only takes 5 cycles. The FMA code is, in fact, going to run significantly faster than the non-FMA code. Okay, this is really easy. Let's go on to something a bit more interesting. So we've got this code now. So on the left-hand side, we're doing A times B plus C times D. Very, very, very similar to the last code, but there's that extra multiply in there. On the right-hand side, we're taking C times D, and then we're calling FMA. Who thinks the no FMA code is going to go faster? Around half-ish. And who thinks the FMA code is going to go faster? Okay, also sort of half and some half-raised hands, too. Okay, I want to try something a little strange here. Now that you know, call it around half and half. Half of the folks think that the FMA is going to go faster. Half of the folks think the non-FMA code is going to go faster. Reflect on that for like 5 seconds. Maybe what you guessed wasn't right. Okay, I'm going to ask again. Who thinks the no FMA code is going to go faster? Okay, it worked. That's an interesting social experiment. Theory of education stuff. Just the fact that you might think, maybe, hang on, do I really? Yes, okay, so let's do the same diagram as what we did before. So on the left-hand side, we've got A times B, and we've got a C times D, and we're going to add the result together. On the right-hand side, we've got the C times D, and then the FMA, where the right-hand, the result of the C times D is going to be the addition to it. The point here is that those 2 multiplies are completely independent. And because there are many multiply units on all chips nowadays, those 2 multiplies are going to happen at exactly the same time. So those 2 multiplies are only going to take 5 cycles combined. Then you're going to add, and that's going to be 8 cycles in total for the code on the left. However, the code on the right, you've got C times D, which is going to take 5 cycles. The FMA has to wait until that multiply is finished before it can take its own 5 cycles to do its thing. The code on the left takes 8 cycles. The code on the right takes 10 cycles. Less cycles is better. Left-hand code goes faster. So this is a case where using FMA is going to make your code go slower. And a lot of this stuff really happens in real code. And that's kind of interesting. So if you're writing code with intrinsics, first and foremost, profile, because you'll know if things are going faster with the FMA. But second of all, you really got to think about this tree of dependencies and what the deal is. I want to end this on a bit more positive note, so I'm going to tell you right now that the FMA code not only goes faster, it goes way faster. So this is code that's just going to do a dot product. It's traditional dot product of 2 vectors, a sub I and b sub I, and this dp variable is just going to calculate the dot product of it. And if you look at the trees are going to be a little bit different. Processors don't really care that this thing is a loop. So when a processor is looking at instruction like this, trying to figure out what it can execute, it will look across loop iterations because it can. So in this case, on the left-hand side, we're able to do a multiply of a sub 5 and b sub 5 at the same time as we're doing the multiply of a sub 6 and b sub 6, which is kind of cool. We're executing, or the processor is sort of looking ahead and doing extra iterations of the loop in parallel with whatever's currently executing. So that's 5 cycles. Then we've got the dependency on that add, and then the dependency on that add. It's 5 plus 6. So the left side takes 11 cycles to do 2 iterations. As opposed to the right-hand side, both FMAs can happen at the same time, right? That's the point. The FMA units, there are 2, I think, on Haswell. So you can do 2 FMAs, 2 scalar FMAs or 2 vector FMAs in parallel. Those can be launched, right? You're going to get results every 5 cycles. So, you know, on the left-hand side, you've got 11 cycles for 2 iterations. On the right-hand side, you've got 5 cycles for 2 iterations. That's more than twice as fast, which is pretty cool. Okay, quick recap. Yes, the right-hand side is faster. So quick recap, FMA is a new CPU features. CPUs all have them now. The latest AMD chips, starting with Steamroller, have FMA support, and the Haswell chips as well have FMA support on the Intel side. It is hard to know when it's beneficial. I promise you it's hard to know. Those are really, really, really simple examples. It's very easy when you're looking at a single line of code to know whether FMA is going to be beneficial or not. When you're looking at code in the context of running it next to other code, things get a lot more complicated. If you wanted to use intrinsics, you have to profile. You have to be really, really careful about this. It gets even more crazy because on AMD Steamroller, the cycle counts are different. Floating point multiplies don't take 5 cycles, they take 6. Floating point adds don't take 3 cycles, they take 6. And FMA doesn't take 5 cycles, it takes 6. So right, the formulas for if you were to want to, you know, write your own compiler optimizer were going to be different for AMD Steamroller versus the Haswell chip from Intel. And if you throw the Arch AVX2, right, we're going to do that analysis for you. So I'm really happy with what my team has done with the Arch with the FMA support, where we're going to make sure your code doesn't slow down. And if you guys do find cases where your code actually is being slowed down by the compiler, I want to know about it. So please come see me afterwards. Okay, that's the end of FMA. I want to make sure you guys are okay with like the pace of this. I know this is totally different than other talks, making services and doing game stuff. So I just want to make sure we're okay. So I see a few nods. So okay, great. Okay. Item number 2 is a statement about performance. I think it is a bold statement about performance, and here it is. Highly optimized CPU code isn't CPU code. So if you guys have seen my past talk at last year's Build conference, you'll sort of have an idea of what I'm getting at with this. But I want to sort of tell a little story as a little technical story, I guess, before getting back to this statement. But highly optimized CPU code isn't CPU code. Okay, so before getting to that, we got to talk a little bit about vectorization. So Arch SSE2 and Arch AVX are going to provide 128-bit automatic vectorization, or you could write intrinsics yourself and get that kind of vectorization. Very, very, very briefly, what that means is you've got a for loop. In this case, let's just say take a bunch of arrays and let's say they're all floating point values, right? You're going to do load b sub I is a single float. You're going to load C sub I that's a single float. You're going to do a single floating point add, and you're going to store the result back into A sub I. When this gets vectorized automatically, or if you were to write it with intrinsics, we're, instead of going to load one element of B sub I, we're going to load 4 elements of B sub I. We're going to load 4 elements of C sub I. We're going to do 4 additions at the same time in parallel, and then 4 stores into A sub I. And the deal is the vector instructions are going to take just as long as the scalar instructions, because processors are really powerful nowadays. And the benefit really comes because you only need to run 1/4 the number of iterations for that loop. And that's why you're going to get the speed up. So for the Arch AVX2 switch, we now do 256-bit automatic vectorization, or you can write intrinsics if you want to. And what that's going to look like is this, where the real win comes because you're doing things 8 at a time instead of once at a time or 4 at a time. And the loop is going to iterate basically 8 times fewer. If you're interested in knowing if a loop was vectorized to 256-bit or 128-bit, pro tip, take a look at the letter of the registers that are being used. If it's a Y, it's 256-bit. If it's an X, it's 128-bit. The names of the instructions are identical in both cases. It's just the register side. I thought that was kind of weird, so I thought that I would point that out. OK, we got to get back to that bold statement, because we're not quite there yet. But first, I got a question. Does 256-bit code run twice as fast as 128-bit code? I won't make you raise hands for yes or no. But no, the answer is no. And the way I like to look at this, I think, is kind of illuminating. So take something that runs for 100 milliseconds. And of that 100 milliseconds, 80% of the time is being spent on the CPU, and 20% of the time is being spent waiting for stuff to come back from the caches or come back from memory, where the CPU is just sort of waiting for stuff to happen. This is a totally reasonable way of thinking about scientific code. 80-20, 90-10, 70-30, where if you're doing scalar stuff, a reasonable amount of time is being spent on the CPU, and that's great. It makes vectorization a candidate for making your code run a lot faster. So let's say we took that 32-bit float code and we vectorized it using 128-bit instructions. This is a little bit simplistic and, in a sense, naive, but it really does get the point across. You can't necessarily speed up memory just by using SIMD instructions. You're going to be speeding up the CPU portion. Right? You're not doing 1 multiply anymore, you're doing 4 multiplies now at the same time, and that's the part that's really going to get faster. If you were saturating your memory units before, vectorization is not going to make your memory come in any faster. If you're already saturating it before, that's what it's going to be. So that's what I've drawn here, where, yes, there is a speed up, a 2.5x speed up, being able to do things 4 at a time, but it's really the CPU portion that's gone 4x faster. And similarly, going to 256-bit, we're making that CPU portion twice as fast. And, it's in this particular case, it's a 1.3x speed up going from 128-bit code to 256-bit code. So the answer, at the very top, does 256-bit code run twice as fast? No, it doesn't. And this is sort of a straightforward, kind of simple explanation why. But there's something really interesting in here. And this diagram is not complete without really, really, really looking at it. And this is where the illuminating part comes in. I think it's illuminating. I think it's pretty interesting. We've started with a scalar piece of code where 80% of the time was being spent on the CPU, 20% of the time was being spent waiting for memory. Through optimization, through taking advantage of 256-bit stuff, we've turned a CPU-bound program into a memory-bound program. So what used to be 80% CPU is now 33% CPU. And that's a big deal. This is what I mean when I say highly optimized CPU code isn't CPU code. It's not anything like that. You're waiting for memory most of the time, right? 66% of the time in this case, you're waiting for stuff to come back from the memory where you can then dispatch the stuff to the CPU and actually do the work. That's different than how people generally think about performance on modern CPUs, right? We've got all these new instructions that are going to make your code run faster, your CPU code run faster. But, right, for something that used to be 80-20, if you're taking advantage of high-performance vector stuff, that's really not where you should be focusing your efforts, right? The efforts should be all on memory. And I'm sort of, I think that's a pretty bold statement. It's not something that people are really saying too much nowadays. It's not really something people are looking at too much nowadays. I mean, if you look at a piece of code, do you really know right away where all the loads are? Right? I don't. When I look at a piece of code, I'm looking for multiplies, divisions, calls to library functions, calls to other functions, right? Square root, sine, cosine. That doesn't matter as much anymore when you're talking high performance code. It's where are my loads? Where's my data coming from? So I gave a talk last year at the Build conferences about native code performance and memory and how memory affects stuff, things like data alignment, cache access patterns, and caches being used in multi-threaded environments, multi-process environments. And all that stuff is definitely important back then, but as we progress into the 256-bit world and beyond, it matters even more. Like what used to matter for 32-bit code, you're talking about 20% of the times being spent in memory. Yeah, you make your cache access patterns better, you're gonna get a better win. But now in something that's 66% memory, that's a huge deal. And I think that's really worth calling out, right? Modern code performance, right? You're talking highly optimized code, you're really talking about memory. And what I enjoy is that if you run your program, regardless of if your cache access patterns are good or bad or whatever, Windows Task Manager is going to tell you you're using 100% CPU, right? And if you've got a highly optimized 256-bit program where, say, like all of your time is being spent waiting on memory, waiting on caches, waiting on memory, waiting on disk, all that kind of stuff, Windows Task Manager is going to tell you you're spending 100% of the time on the CPU. That really is just wrong. You know, it may have been true back in the day, but it's just not right. You know, if you do the same thing with vTune, it's going to give you way more illuminating information. This probably can't read it, and I know it's confusing. You sort of have to work with vTune for a while before you learn the language. But right at the very top, so I ran, there's the N-body simulation. You guys have probably seen it. I made sure it was highly optimized for 256-bit. And yeah, 70% of the time was being spent waiting for memory. And this is what vTune actually told me. So forget about the Windows Task Manager saying 100% CPU. I've got vTune right here, the first sentence. A high number of CPU cycles is being spent waiting for the last level cache load misses to be serviced. It's telling me you're waiting on memory. It's right there. You just got to know to look for it. I think that's pretty neat. Okay, if you were worried that things were confusing or things were getting a little bit out of hand, we're going way off the deep end for number 3. So get ready. So this came from, I was working on AVX2 support in the compiler, and we do a bunch of performance analysis to make sure that things are going to actually speed up. I was doing some performance analysis on a template math library called Eigen. That's their logo. The logo is adorable. He's the owl professor. He's got, I didn't notice this for like the first probably dozen times I looked at the logo. He's got an identity matrix in his fur. And he's got a lambda on his hat. Huh? Yeah. It's one of those things. I don't know if you did, I only learned this recently. The new Microsoft logo has the 4 squares, right? You know, the standard 4 squares. There's a red square, there's a blue square, there's a yellow square, and there's a green square. That's Xbox, Office, Bing, and Windows. I don't know if you've noticed that, but the blue in the Microsoft logo is the Windows blue. And the yellow, and right, that kind of thing. It's sort of one of those cool-looking logo things that you really got to spend some time and look at before you really appreciate. Anyways, that has nothing to do with this. We found a performance problem when you throw the Arch AVX2 switch for a particular micro benchmark using the Eigen library, where you compile with Arch AVX2 and your code runs 60% slower than if you did it with Arch SSE2. That's crazy. Yes, that's big, you know, red lights flashing everywhere. Hey, we gotta really dig into this. So I spent some time and dug in. And the thing that really helped me understand what was going on is this key piece of information that the slowdown also happened if you throw Arch AVX. And that's really useful for me because I can then take an AVX binary and run it on more machines than just an AVX2 binary, which for now is only going to run on Haswell. AVX, I can run it on some AMD machines, I can run it on a whole bunch of Intel machines, and just sort of get more information. And I did that. So these are some of the results that I saw for this. I took 2 different binaries, one compiled for SSE2, one compiled for AVX, and I ran it on Sandy Bridge and I ran it on Haswell, and these are the results. And there's a few things in here that are sort of good to know. So I took an SSE2 binary, ran it on Sandy Bridge, and then took that exact same binary, ran it on Haswell. It went faster. Good. The Intel guys, they're great at making chips, right? All processor manufacturers are great at making chips to take existing code and make it run faster. That's an interesting data point there. Another interesting data point, well, sort of kind of interesting, okay, it's not interesting at all, is going from SSE2 and recompiling it with ArchAVX, this particular microbench, or this particular benchmark, didn't really change. Right, Sandy Bridge is the first AVX machine that Intel produced. When we compiled with ArchAVX, we didn't really get a win, we didn't really get a loss. It's sort of like, eh. So that's what that arrow's for. But this is really what I want to talk about, right? Take the SSE2 binary, run on a Haswell, runs really fast. The AVX one runs super, super, super slow. That is terrible. Let's really, really dig in and find out what's going on. The first thing you got to know is what data structures are being used. I've distilled the problem into something a bit more manageable that can go on some slides. And this is the data that's being consumed. We've got a struct, and the struct has 2 fields. Each field is a vector with 4 floats in it, right? Overall, this is 256 bits of data. And then we've got this function called func2 that does a bunch of stuff. It then calls another function called func3, and then does a bunch of other unrelated stuff. And then these are those two consecutive 128-bit copies. And when we throw the ArchAVX switch, we're replacing those 228-bit copies with a single 256-bit copy. And I went through the code and dug into this and found that this was the thing that was making the code run 60% slower. What's really interesting is it only ran 60% slower on Haswell. There were no performance problems doing it on Sandy Bridge. There were no performance problems doing it on AMD machines. That's kind of weird. And this is going to get sort of the juices flowing when we got to think about what does it mean to reason about performance on modern, like super, super, super modern processors. So let's say you guys were working on this. You found this particular thing, this particular optimization, replacing 228-bit copies with a single 256-bit copy caused the performance slowdown. What do you do to get more information? Call Intel. You know, it's funny. Well, so you stole my joke. So, right, the thing that anyone can do is you profile it, right? That's what you would do here. Yeah, I didn't profile it. I sent an email to Intel asking, please, I need help, I'm really busy. But anyways, so what Intel did was profile it, and this is what they came back with. Right at the very top of the vTune report, it said, loads blocked by store forwarding. And if you dig in a little bit deeper, if you can read vTune and how it presents information to you, it tells you right there that loads blocked by store forwarding is causing this regression. It's in red, the blue bar is nice and wide. That's where the time is being spent, is in dealing with things in the store buffer. Anyone heard of the store buffer? It's a part of the CPU that is my favorite part of the chip. I saw 3 hands go up. This is good. This is good. Okay. Like I just said, store buffers, my favorite part of the chip. We're going to spend just a minute and explain what they are because it's critical for this. Yeah, store buffers are awesome. They really are awesome. All the physical nature of a store buffer, it's a small piece of hardware that exists on each core. It just keeps a small cache or a small table of store instructions and what data they're going to be stored to. So you got store instructions coming in through the pipeline. It just keeps track of the store instructions as they've come in, such that when a subsequent load comes in and requests data from that particular address that you've already stored to, the load does not need to go to memory. The load can totally bypass the rest of the memory system, doesn't need to go to the caches, it just gets the data forwarded right from the store inside the store buffer. Store buffers are extraordinarily important for performance, especially because high performance, highly optimized CPU code is really being spent waiting for things to come back from the caches. The store buffer is going to enable certain loads to skip the caches and leave that extra bandwidth for other loads that might actually need it. And when we're talking about things becoming more and more I/O bound, more and more memory bound, this matters even more. So store buffers are really, really cool. But there are some restrictions in what you can do for that store to load forwarding. So for example, if you've got a collection of small stores, like let's say you've got 4 consecutive 1-byte stores, and then you've got a 4-byte load that's supposed to overlap all of those stores, that does not get forwarded. The logic of doing that in hardware is just I guess they just don't do it, and that's going to cause a store buffer stall. That's just one example of many of the restrictions for load to store forwarding. There are pages and pages and pages in the software optimization guides that tell you all of the reasons why you won't get store to load forwarding, which is kind of crazy that there's pages and pages of this instead of it just sort of working nicely. And you know, the term restrictions doesn't really capture what happens when you have a problem in the store buffer. You can't really use the word bugs because they're not really bugs, right? There are certain requirements when you're actually making hardware. You can't make everything work, we know that. So bugs doesn't really work. I like the term deathly potholes. So you're going along nice and great, and then you hit a store buffer problem, and your performance just goes down the drain. And that's sort of how I felt dealing with this particular store buffer issue when profiling this particular micro benchmark. Okay, so let's dig in. This is the more complete example. This is the code that has everything you need to know to find out what's really going wrong here. So we've got really 3 functions. There's func1, there's func2, and there's func3. All func1 does is it just, in a tight loop, calls func2, which does some stuff, calls func3. Func3 does some stuff and does 128-bit load, and then yada, yada, yada. So bear with me, because this is what actually happens from the store buffer's point of view. You got an iteration of, take I equals 100, right? We then call func2 calls func. Does unrelated stuff, calls func3. Func3 does its stuff, it returns. We're back in func2, we do some more unrelated stuff. There is our 256-bit store to X. So there's our 256-bit store to X. Func2 then returns. We go back into the context of func1. We check that we do I++. It's now 101. We do the check to make sure it's still less than 10,000. It is. We call func2, actually calling it. Inlining doesn't come into account here. We do some unrelated stuff. We actually call func3. Func3 does some unrelated stuff. And then that's our 128-bit load that's causing the store buffer problem with that 256-bit store 4 function calls ago and 1 iteration of the loop ago. And this is actually what happens for this particular bug. I've got the assembly instructions here from the processor's point of view. So these are the dynamic assembly instructions of exactly what I just said. So at the very, 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 very top, we've got that 256-bit store. And then func2 returns, we increment I, we call func2, we do a bunch of unrelated stuff, we call a security cookie check, we call a different function that does something different that's not even written here. We do a ton of register moves, we do a ton of other loads and stores, we do a bunch of other stuff. We then eventually call func3, do yet more unrelated stuff. And then there's that 128-bit load at the very, very, very bottom. There are 40 assembly instructions between the store and the load. We're talking 3 different functions and 2 different iterations of the loop. And this loop has nothing to do with the store and this load. The for loops in a function that's just calling it. That's crazy. how can you reason about performance like this when you can get store buffer stalls causing 60% performance problems from functions that are really far away from one another? That's an actual question, by the way. I don't have a very good answer for it. And that's what it really means to do performance work on modern architectures, right? So here's something to keep in mind. The Intel Haswell chip can execute at peak throughput 8 microops every single cycle. So sort of kind of 8 instructions every single cycle it can dispatch at peak performance. Not only that, but the instructions that it can dispatch are out of order, and as it reads, future instructions, it looks at future iterations of loops, it does that kind of stuff. It can look up to 60 microops ahead to determine how many, up to 8 of those we can dispatch at once in a single cycle. When you're talking 60 microops, you're talking multiple functions. You're talking many, many iterations of tight loops that all of a sudden you're now, you're looking at secondary effects, things like store buffer stalls, store buffer problems, you name it, where previously you only had to really think about that stuff in the context of a single function. Well, now you got to sort of think about it in the context of the code that surrounds it, plus or minus a handful of function calls, plus or minus a handful of loop iterations. That's pretty crazy. I think it's pretty crazy. So I want to do a sort of a recap of this, because I know this is really confusing. But basically, we're talking, this is just a normal optimization. Look, the chips now support 256-bit instructions. We should be taking advantage of that. Well, that's what we tried to do here. But it then caused the problem in the store buffer. The store was absolutely nowhere near the load. I cannot stress that enough. It's a huge deal. And yes, this caused a 60% regression in the micro benchmark, and it only reproduced on Haswell. Didn't reproduce on Sandy Bridge. Sandy Bridge can't look that far ahead. It's cool, right? The processors nowadays are getting so powerful that all these secondary effects are growing in scope. The cool thing is you've got profilers to help you with, at a minimum, diagnose what's going on, or the phone numbers of someone who works at Intel who can help you with that. But really, the performance landscape is changing. Right? We can't just think about a single function. We can't just think about normal, old-fashioned multiplies and adds anymore, right? There's a lot more that's going on. And the only way to move forward in a sort of sane way is to get to know your profiler, to get good using vTune, get good using CodeXL, get good where it's appropriate to use the Visual Studio Performance Analyzer. It's the only thing that's going to help you get through this type of stuff. Okay, so quick recap. This is that timeline slide again. And again, things happened between 2001 and 2011. It wasn't like everyone just went to sleep or something. And yes, so Haswell has AVX2 support. Some future AMD chip may or may not have some future AMD chip will have AVX2 support. That's as much as I've been told, so that's what I put up here. And more is coming. AVX 512, so on and so forth. Vector registers aren't getting any smaller. Why would they? So these types of problems that we're looking at now, the 3 things that I went over today, they're just going to get more interesting. The processors are just going to get more powerful. The 3 things we spoke about, new CPU features, right? FMA on paper sounds free. You can do a multiply and an add in exactly the same amount of time it used to just do a multiply before. You get this extra free, and I like free stuff, so let's go and do it. But it's not that simple. I think is kind of cool. The statement about performance that highly optimized CPU code isn't, it's really a matter of focusing on memory, and anywhere you can divert resources for performance work to make memory better, to make cache accesses better, to reduce your working set size, to keep hot data, so not hot code, but hot data, things that are accessed together, keep them together in memory as opposed to spreading them out, that type of stuff is super, super, super important, and it's only going to get more important as vector registers get wider, as CPUs get faster. And then And then that awesome store buffer issue, where normal optimizations can have pretty crazy secondary effects on powerful CPUs. And it's only going to happen on powerful CPUs. And again, it's only going to get more interesting as CPUs get more powerful. So one extra thing I wanted to mention about that, the Visual Studio 2013 Update 2, which you guys can get now, does have that bug still where we have that 60% slowdown in that particular eigen micro benchmark. We're going to fix it, but right now we haven't yet. We've done all the FMA work, and FMA stuff is definitely great with what we've got now. But be advised, we're going to be making some changes to that particular optimization that combines 128-bit stores or 128-bit copies into a single 256-bit copy, because that's not cool. Great, you throw the Arch AVX2 switch, you want to be able to get performance on AVX2. You shouldn't expect any kind of slowdown. That's not cool. They've asked me to show this slide. You've probably seen it with all the other talks. You, as MSDN Ultimate subscribers, you get some free stuff, I guess, as part of the VS Partner Program. And I wanted to leave you with two points that I will stress to no end. Point number one, profile your code. Always, always, always profile your code. Item number two, profile your code. Cannot stress that enough. Yes, number three, profile your code. Don't stop profiling your code. Okay, thanks. So that's the end of my talk. Here's that QR code thing for evaluation. I'll be happy to take questions. I'll be sticking around here for a little while, and then I'll be outside for folks with more questions afterwards. If you do have questions, please use the microphones in, I guess, the center aisle.
So, about profile your code. So, the last part of your talk talked about how, so if I had taken that code and profiled it on Sandy Bridge, I'd have been meh, but not caring. So does that mean that not only I have to profile my code, but I have to keep every CPU that, that my product is ever going to run on and profile it on every single one of them? Or is there something easier I can do?
Is there something easier you can do? I wish there was.
Or
I don't know. You tell me.
Is there a representative subset of CPUs that are going to cover the 90% case, so I don't have to have, 85 machines sitting in my cubicle?
Yeah. So that's a great question. Thanks. It's Jonathan, right?
Yeah.
Okay. So you're definitely asking the question to the wrong person. I have one of every CPU type sitting in my office, laptop and desktop portion. I'm also a huge microarchitecture geek, so I just love that stuff. Mm-hmm. So of course, my answer is going to be, yeah, you better know the impact of your floating point code when you run it on a Jaguar processor, right, where you've got two cores that are sharing a single floating point unit, compared to running it on a Haswell machine, right? But that's just me.
And
so sorry, I can't give you a better
answer. And the
answer.
other question I have is, do you have a good, you showed AMD and Intel, do you have a good choice for ARM for how to profile?
Very, very, very good question as well. If you find one, let me know.
Hi. What about the backend profiler with .NET, now that the .NET native is using your compiler, your backend compiler? I mean, I can't imagine .NET developers all using VTune and going deep and so on. So what's the best practice is it to measure this kind of stuff on .NET?
Okay, so thank you for the question. I've been working on .NET native stuff for a little while now, and working with the team who's been doing the code generation and optimization for it. This is funny. I've been in VTune and CodeXL debugging C# applications, profiling C# applications, and it does work the same way. Unfortunately, there's that extra level of indirection, right? So, a lot of the .NET native stuff is turning what looks like C# code, or it is C# code, into something not as C#-ish. So, where runtime checks are inserted in C# code to make sure that your array access don't go out of bounds, we're going to be removing that, right? We're going to be optimizing your code in such a way to make it sort of look as native as possible. That is, that's going to be difficult to profile and sort of debug and rewrite your code end to end. I'm going to get in so much trouble for saying this. If you got performance-sensitive code, why are you writing it in C#?
Yeah, I mean, I can't imagine everyone outside. I love C++. I write so many code in C++, but I mean, I can't imagine every .NET developer going there and say, okay, let's use vTune and see what happens. I don't even guess they can understand really the blue bar, what's going on, if there is a problem or not. So I mean the average developers outside there.
Okay.
It's not reasonable. So.
Okay. I mean, I don't want to do anything like compare sort of an average C++ developer to an average .NET developer or anything like that. Right? The profilers aren't that. It helps to have a college degree in microarchitecture to be able to use vTune. It is not a hard requirement. Right? vTune will tell you the top features of the chip that are causing problems, or the top portions of your code that are causing problems. It's definitely going to be a start. I wouldn't be worried about folks profiling their code. I want people to profile their code. Okay. Thanks for the question.
Hi, I've got a question on optimization for power. I mean, I think on battery-constrained devices, phones, tablets today, optimizing for performance is one thing, but optimizing for battery life is probably a lot more important. The cost of writing to memory is a huge hit in power compared to an add or a multiply. What are you guys doing on the compilers to optimize for power?
Great question. What are we doing to optimize for power? So, I am going to give you an engineering answer. This is not an academic answer, because the academic answer just doesn't really apply right now. So when you talk about power, it's not just the CPU, it's not just the memory units, it's really the power of the whole system, right? Power is sort of an end-to-end type of thing. And what I've come to learn is to get power efficiency on a system, have the processor do whatever it's doing as fast as it possibly can so it can go to sleep. And if we can make an optimization that, say, decreases power consumption by 10%, you take a 1-watt chip and you make it run at 0.9 watts, that's nothing compared to getting your code to run to completion so that 1 watt goes down to standby. So the engineering solution for now has been make the code run as blazing fast as possible so that the CPU can go to sleep. And on ARM, so this was something that I had wrong when I started working on automatic vectorization. My understanding a few years ago was that on ARM chips, if you're using the Neon instruction set, for a phone, you're going to burn a hole in your pocket if you're doing vectorization, if you're doing signal processing or whatever, that the chip's is going to light on fire and you're going to hurt yourself. That is not the case. Absolutely not the case. Using vector instructions on ARM is going to make your code run faster, it's going to make your processor go to sleep, which is going to improve the system battery. Now, at the same time, yes, there's things that we could do better. One of the things you mentioned is less writing to memory. Well, good news, less writing to memory is going to make it run faster too. Yeah. But seriously though, right, I would love to see something that we could do to change optimization that are going to make a huge, huge difference in terms of the system power. I would love to be able to do that. Right now, we're really focusing on things like code size and code performance. So we want to be able to minimize disk access. We want to be able to minimize working set. But again, those are things that are going to make code run faster in a system as well. Yeah. So I give really long-winded answers.
No, that's okay.
That
I mean, no, that all makes sense. I suppose I'm thinking of things that are specifically targeting different cache architectures on different platforms. You talked about the differences between Haswell and Sandy Bridge, etc. I just wonder whether you guys look at different cache architectures in terms of your optimizations at all?
Okay, so you seem like a really cool guy. I want to talk to you about this afterwards.
Okay.
And that's me deflecting your question because I don't know the answer.
I have a question regarding how this plays into PGO. The thing that I'm thinking about is you have a training set that you play back and exercise your code paths that you consider are critical. And now that you mentioned that the memory access latency could be a significant factor, if you do detect that it is actually playing a role in the LLC miscounts going above a certain threshold, can you use that as a feedback and throw that as a, okay, there is something that's wrong, which may be a signal to the devs to look at more closely and then maybe consider, I don't know, what to emit in terms of making the code path or optimize the memory access
Right,
patterns
okay.
a little differently.
Great question. So for those who don't know, PGO is Profile Guided Optimizations. It's a technique where you run your code that's been instrumented to capture profile counts of what part of your code is hot, what part of your code is cold, along with a whole bunch of other information. Then you recompile your code with those counts as input, and the optimizer does certain things differently based on those counts. That's POGO, PGO. Does that stuff come into account in terms of memory? Yes, absolutely. One of the big things that we've done recently with POGO is to, okay, so I'm going to answer two different questions in two different ways. This is the first one. So POGO definitely does working set computations. We profile data that's generally accessed together, and when your code is going to get optimized again, we're going to put that data together and basically do hot-cold data separation, sort of in phases, if you will. So if some part of your program, your working set's going to be looking like this, we're going to make sure that this thing is all going to be in the same chunk of memory, and everything else is going to be cold with respect to that. And then at a different part of your program that's running, this chunk of memory is going to be used, so that's the chunk that goes together. So we've definitely focused a lot on working set stuff, and that will absolutely help reduce, right, you reduce the overall hot working set of your data to, you know, minimal number of memory.
Or even suggest that if you co-locate them close enough, will that offer benefits in terms of cache prefetching?
Yeah, so yes. Yes, absolutely. So we definitely are looking at working set stuff, and we've made some improvements to the working set portion of POGO, of PGO. Okay, the second part of your question is, can we give that feedback to the user? And not just for working set stuff, but for more in such a way that, hey, POGO tells me certain things about my code like this, maybe I should rewrite it in such a way. We're looking into that. That's something that's like the holy grail of optimization stuff, to be able to give the user actionable feedback. Actionable being kind of a funny word. But right, give the user feedback that they can take such that they will know if they do these things, or look at these things and look at this part of the code and rewrite it, that your code's going to run faster. We're looking into stuff like that, absolutely. I think it's super, super, super cool. I want to do stuff where data gets tracked. I have no idea how to do this, how to actually implement it. I've just been thinking about it for a long time, where we could somehow, you know, you've got your memory space, imagine it as this giant blob, and we sort of create maps of data, right? So through your program execution, we know that this chunk of data that's here goes into the stack, and then it goes into this part of the heap, and then you add it with this resulting data, and it goes into this other thing, and it sort of creates this map of where your data lives in the actual memory space. To present that to the user as part of profiling data, I think would be amazing. And that would probably take care of a lot of these issues. You would be able to look at your program entirely from a memory point of view. And if memory is really important, and I think it is, it's almost like the code doesn't matter. Right? I don't care if I'm doing a multiplier or call to square root or dividing stuff. None of that really matters anymore. I just care about where my data is coming from and where it's going. And I'd like to be able to give the users that information, which I think is sort of what you're asking. So I've definitely been thinking about it, but it's, yeah, I don't know how to implement it yet.
Okay.
If you got ideas.
No.
Okay. Thanks. Anybody else? All right, I'll be outside if folks have any more questions.